How's it going? This is Mr. Cook. I'm going to be going through some of the stuff from section 2, 2.1, operations of polynomials. So by operations, we mean that we're just going to be adding polynomials, subtracting them, multiplying them, and dividing them, and seeing what we have after that. So we'll probably get through this first page of odds, or a good chunk of these problems first, and then go through some long division, maybe in this video, maybe in another. We'll see how long the video gets to. Anyways, so the first part says to state whether the function is a polynomial or not. So you know if something is a polynomial if it's a bunch of terms that are adding and subtracting with each other. And by terms, I mean monomials. So a monomial is, you know, any numbers and collection of variables that are multiplying together, as long as the variable is not in the denominator, and as long as it's not under like a radical or a fraction exponent, then that makes it a monomial. So, like for example, just briefly, if I see an x in the denominator on any polynomial or any potential polynomial, like if I saw like 4 over x or any x in the denominator, that means that we don't have a polynomial, because this makes it not a monomial, it makes it something else. Okay, so watch out for x in the denominator. If you see that, then you know for a fact that you don't have a polynomial. Another thing is if you have, you know, any number, but if you have any variable value with a fraction exponent, like 5/3 or 2/3 or 1/8, whatever, any fraction, then you know for a fact that you don't have a polynomial any longer, because this is not a monomial term. And then the last thing is any type of radical symbol. So if I had like a 22, and then like if I had a radical x or square root of 3x or something like that, or if it was a cube root or a fourth root or whatever, any type of root also means that I don't have a polynomial. But other than that, you know, I will have a polynomial. So let's go by real quick and say which ones of these are polynomials and which ones are not. So -5 is a polynomial, believe it or not, because it has a single monomial on it right there. So since I have this monomial, this -5, this constant value, that means that yes, this is indeed a polynomial, because it doesn't break any of these rules that we talked about a little while ago. If it is a polynomial, give the degree and also the number of terms. So terms, we can tell how many terms there are by the number of monomials that are separated by addition and subtraction, okay? So we just look for like the numbers that are in between and outside of the addition and subtraction. That's what tells us how many terms that we have. So in this case, we just have a single term because we just have a single number. So that means that we have one term. Oops, not term. There we go. Okay, one term. And then if we want to talk about the degree, that's just the exponent power. And when we talk about degree of a polynomial, we're looking for the biggest exponent power. So we'll, you know, take a look at some of these and we'll see exactly what that is. Especially for number 5, we'll be able to take a look at it. But there is no exponent power here, so that means that this is a degree 0 polynomial. It's just a constant value, and that's it. Number 3, is this a polynomial? Well, we have x in the denominator. Since we have x in the denominator, this means that this is not a polynomial. And the reason that it is not a polynomial, because we have to say why if it's not, is because there is x in the denominator. And that means that we don't have a polynomial right there. All right, the next one, number 5, I don't have any variables in the denominator, don't have any variables with fraction exponents, don't have any variables under any roots or anything like that. So that means that this is a polynomial. All right, so that's pretty easy. And then the number of terms, that's another thing that we need to list off. So that's how many of these monomials are in between the addition and subtraction. So we have one monomial here, another one here, another one here, another one here, and another one here. So that's 1, 2, 3, 4, 5. 5 terms. So that's pretty easy to count as well. Just circle all the stuff that surrounds the addition and subtraction symbols, and you know how many terms that you have. Next, we need to talk about the degrees. That's the biggest exponent power on all of the terms. So if we just look at all the exponent powers, we've got 4 here, 3 here, 2, and then even though a doesn't have it, it's a 1 right there. That's always hidden there. And then this would technically be a to the 0 power. So the biggest of all the powers is 4 right here. So that means that the degree is 4. So this is a degree 4 5-term polynomial. So that's how we do the first 3 questions, and tell whether or not they're polynomials, and their degree and the number of terms if they are polynomial. The next part is pretty easy. This says to simplify each expression. So this is where we start up the operations part of it. We're going to be adding, and we're also going to be subtracting polynomials. So when we add polynomials, it's really, really easy. So adding in between the 2 polynomials, so this is the first polynomial, this is the second one. If we're adding them, all we need to do is just get rid of the parentheses and combine like terms. So we just combine like terms here. All right, so get rid of the parentheses. I've got 4n to the 4th minus 3n to the 3rd plus 3, and then plus 8n. Plus 6n to the 3rd minus n to the 4th. So what do I mean by combine like terms? I mean that whenever that you see an exponent on a variable, and it's the same exponent, same variable, like this 4n to the 4th here, and this minus n to the 4th, since they have the same variable and same exponent, I can combine their lead coefficients. So what this is saying is that I can combine these 2 together by just simply adding the numbers that are in front of them. So I've got 4n to the 4th, and I'm subtracting 1n to the 4th. So if I take 4 and subtract it with 1, that gives me 3. So I've got 3n to the 4th powers. I like to organize these, and I like to put shapes around my like terms, so then I can keep track of like what I've added, what I've subtracted. So I've already taken care of the 4th power ones. Now I'm going to circle all the ones that have 3rd power on them. So negative 3n to the 3rd power. I have another one over here, a positive 6n to the 3rd power. So if I have 6n to the 3rd powers and I subtract away 3 of them, I've got 3 left over. So I've got a positive 3n to the 3rd power remaining. The next one I have is, let's go with the n, just n to the 1st power. So I have 1 of these, so that's going to be 8n. And I don't have any other just n's by themselves, so that means that it's just going to be, just that regular old 8n that I have. And then the last thing that I have is this constant, so plus 3, and that's the last of all of the values that I need to add up. So this is my polynomial that I have as a result of adding the 2 polynomials together. The next thing I'm going to do is subtract. So if I'm subtracting polynomials, I need to keep the parentheses on for one quick little thing, and then I can remove them and combine like terms. So what I need to do first, before I get rid of the parentheses, is distribute this negative. So distribute the negative on every single term that you have in here. So when I say to distribute a negative, what I mean is that we're going to change the signs on all of these terms inside of the second polynomial here, the one that we're subtracting away. So the first one I can just leave alone. It just stays the same. So I can get rid of the parentheses on that. So I have 4a minus 7a squared plus 6a to the 3rd power minus 5. And then if I distribute the negative in there, I get the negative, the opposite of 5a to the 3rd. So that's a negative 5a to the 3rd. I distribute the negative into this negative 2, and that negative 2 changes signs, so it becomes plus 2. The negative a squared also changes signs because of that subtraction sign, so it becomes a positive a squared. And that negative 7a also changes signs, so that's going to turn into a plus 7a as well. All right, so now we're going to, now that we've distributed the negative, we can get rid of the parentheses, and we just combine all of the like terms. So I'm going to start over here on the left. I've got 4a. So let's see where else we have just a regular old a. That's right over here with this plus 7a. So if I take 4a and add on 7 more a's, I have a grand total of 11a. Now let's just go in order. So I have negative 7a to the 2nd power. Let's see where else I have an a to the 2nd, right here. So I've got negative 7a and I've got 1a. So if I take 1a squared and I take away 7a squares, I'm left with negative 6a squares. Now I'm going to move on to the a to the third power. So I have a positive 6a to the third, and over here I've got a negative 5a to the third. So if I have 6a to the thirds and I subtract away 5 of them, then that means I'm only left with 1a to the third power. If you wanted to write that down as just simply a to the third, that's the same thing as putting 1a to the third. And now we have our constant value, so I've got a negative 5 and a positive 2. If I take 2 and subtract away 5, that gives me negative 3. So that means that I've exhausted all of my different terms, and I've got my polynomial. One thing that'll get you some extra points, not like literally like extra credit points or anything like that, but just, one thing that you'd want to do is write this up in a standard form as well, which means that you're going to put these all in descending order from the greatest exponent power, so the greatest degree, all the way to the lowest one, which would be this negative 3. So here's how I'd write it up. My a to the third goes first, and then I go a squared, so minus 6a squared, and then plus 11a, and then minus 3 at the end, because that doesn't have an a on it. So this is writing it up in its standard form, its proper form as a polynomial, just in a descending order for the powers. All right, the next thing that we're going to do is the product, and this is just regular old foiling, as some might call it, or as I like to call it, because foiling is restrictive to just binomials. I like to just call it the distributive property. So distributive property, that's what it's really called. Just, foiling is just a nice little name that people tell you to remember the process, but distributive property is actually what we're using here. So if I were to use the distributive property on this multiplication of two binomials, what I would do is I'd take the 8b and I'd multiply that. I'd distribute it into the 3b and also the negative 3. So I just multiply the two of these together. So I take 8b and multiply that by 3b. So I multiply the numbers together. 8 times 3, that's 24. And then I multiply the b times the b, which gives me b squared. And then now, so that's the first set of multiplication. Now I do 8b times negative 3. So if I take 8b times negative 3, 8 times negative 3 is a negative 24. And then I still have that b that's attached to it as well. So the second part of the distributive property that I need to do is distribute this negative 6 into both of these terms. So if I take negative 6 and multiply by 3b, negative 6 times 3 is a negative 18. So I have negative 18 and then 1b value right there. Now I take negative 6 and multiply times negative 3. A negative times a negative is a positive, and then 6 times 3 is 18. All right, now that I've distributed everything in there, now I'm going to combine like terms just by adding everything together. So let's see, we only have 1b squared, so that just stays the same, 24b squared. We have a negative 24b and a negative 18b. Negative 24 minus 18 is going to be a negative 42, so negative 42, and then b is the only value there because we're not multiplying, so we don't need to multiply the b's together. It's just negative 24b and then going down another 18b. And then we have that constant value of plus 18 at the very end, and we've combined all the terms together that we can, so this is our finished polynomial. All right, now we're going to do the same thing for number 13. It doesn't look the exact same, but it actually is, because when you take something and you square it, what you're really doing is multiplying it times itself. So that's what square means. So we're going to take 5r minus 2 and multiply that by another 5r minus 2. Then it's the same steps that we did over here. We're just distributing. So I'm going to fast forward this a little bit. 5r times 5r is 25r squared. 5r times negative 2 is a negative 10r. Negative 2 times 5r is another negative 10r. And negative 2 times negative 2 is a positive 4. So after I combine like terms, I get my answer for this one, 25r squared minus 20r plus 4. So there's our polynomial for that. Nice quadratic with 3 terms. The next one I'm going to distribute again. So this is a trinomial. It's already a quadratic, and then I'm multiplying that by a binomial. So I distribute again. So I take 5x squared and I distribute it into the 4x and then also the 5. So 5x squared times 4x, 5 times 4 is 20, so 20. X squared times x gives me x to the third power, so that's one term. 5x squared times 5. Well, 5 times 5 is 25, so that gives me 25x squared. All right. Now, one way that I like to organize this is that every single time that I do one part of distributing, especially with like ones that I've got a ton of terms that I need to distribute in, I like to just put them in like rows and then combine like terms. That's just my preference. If you want to do something different, or if you can just do it all in one straight line, that's fine. But I like to just do it this way. So the next thing that I would do is take negative 4x and I distribute that into both of my terms. Negative 4x times 4x. Well, negative 4 times positive 4 is a negative 16. And then x times x gives me x squared. So I've got negative 16x squared. Negative 4 times positive 5. So negative 4 times 5 is going to be a negative 20. So I've got negative 20x. So that's my second grouping of distributing in. Now the last pair that I need to distribute, now the last number that I need to distribute is the 6. So 6 times a positive 4 is going to be a positive 24x. And then 6 times a positive 5 is going to give me a positive 30. Now I'm just going to combine all of my like terms. So I don't have any other x to the thirds, so that means that 20x to the third is the extent of that term that I'm going to use. I have 25x squareds, and I have to subtract away 16 of them, so that leaves me with 9. So I've got 9x squared. And then a negative 20x plus 24x is going to give me a positive 4x. And then this last number, this 30, doesn't have any other constant values, so it's just going to be a positive 30 at the end. So there's my last polynomial. All right, so that's the first page of 2.1. Now we're going to take a look at the odds for the second page on a separate video.